atmosphere is actually streaming all the way out. It bathes all of our planets on the way to the very edge of our solar system. In fact, it shapes our very place in space.
A statement from educator Carlos focusing on Durham School. I've committed my whole calling to empowering and expressing hypotheses about the universe. Then this happens, the theory is being scrutinized. I embrace this test since it is through such investigation that we advance and make strides in science. The James Webb Space Telescope is fundamentally upsetting several long-held beliefs in cosmology that have been viewed as truth for an extensive time. Another ultra-deep field image has revealed that we have made mistakes in astronomy. The telescope, which was expected to uncover the first stars of the universe, is proving to be truly groundbreaking. The past perspective could present a totally new, profound viewpoint. Not all experts are troubled by these new revelations. Many welcome these advancements, as it has long been clear that there were problems with previous theories. The peculiarities in studying the universe's rate of expansion alone should have raised alarms for researchers long ago. Instead of addressing these warnings, many adhered to outdated theories. The cosmic microwave background radiation, CMB, the oldest light in the universe, was created around 380,000 years after the Big Bang, when the universe had sufficiently cooled for electrons and protons to form stable hydrogen atoms. This phase transition, known as reionization, made the universe transparent to light. The CMB was first identified in 1964 by American physicists Arno Penzias and Robert Wilson. While working on new radio communication technology, they detected a persistent noise coming from all directions. This discovery was considered strong evidence for the Big Bang theory. Penzias and Wilson were awarded the Nobel Prize, and their findings became a cornerstone in the history of space science. The CMB likely provides a brief glimpse into the early universe, with minute temperature fluctuations offering critical insights into the conditions shortly after the Big Bang. Scientists used the CMB as a reliable indicator to measure key aspects of the universe, including its expansion rate. In the late 1920s, Edwin Hubble had already observed that distant galaxies were moving away from one another, and that their speed was proportional to their distance, a relationship now known as Hubble's law or the Hubble constant. Although Hubble's estimates were not as precise as those available today, they were groundbreaking. When the CMB was discovered, researchers recalculated the expansion rate, finding it to be significantly lower than Hubble's initial estimate. Subsequent recalculations using Type Ia supernovae as standard candles provided more accurate estimates, though discrepancies remained. The difference in expansion rate estimates has been known since the 1990s. Scientists have hypothesized issues with the CMB data analysis methods or even the possibility of general cosmological evolution. This discrepancy, known as the S8 tension or Hubble tension, suggests that our understanding of the universe might be fundamentally flawed. Since the James Webb Space Telescope, JWST, began operations, it has provided astonishing data that could help resolve the issue. Some galaxies are so old and developed that their formation may have begun before the Big Bang, challenging established cosmological theories. Astronomy now faces what is considered the greatest crisis in modern cosmology. The universe's expansion speed and the origins of cosmic structures are under intense scrutiny. New images reveal a universe that differs significantly from previous models. The S8 tension has served as an early warning to scientists who continue to adhere to outdated theories. They are now grappling with the possibility that our understanding of the universe may be incomplete. This uncertainty has left many researchers disheartened and perplexed. To address this crisis, it is essential to understand how science operates. Theoretical scientists rely on mathematical models, observational data, and logical reasoning to draw conclusions. Their knowledge evolves from studying anomalies, experimental results, and speculative analysis. The term theory itself implies continuous improvement and refinement rather than absolute truth. Our scientific understanding comes from data provided by telescopes, sound waves and radiation gathered by radio telescopes, and observations from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to separate the most distant light into individual wavelengths and analyze it in detail. It can reveal the elements present in distant galaxies billions of years ago, their mass, and the number of stars they contain. However, Webb's images may have limitations. For instance, it cannot always distinguish between galaxies and black holes, as both can produce similar phenomena due to gravitational lensing. Our understanding has evolved to accommodate various possibilities, often rejecting alternative explanations prematurely. New discoveries from the James Webb Telescope offer critical clues that could lead to replacing old theories with new insights. Researchers are already wrestling with these revelations, which seem so extraordinary that finding clarity will require significant effort. The data gathered from the James Webb Space Telescope, JWST, challenges long-held assumptions about the early universe. Galaxies that appear to be fully formed at unexpectedly early stages defy predictions from the standard lambda cold dark matter, lambda CDM, model. This suggests that galaxy formation and evolution may occur far more rapidly than previously believed. The presence of massive, mature galaxies existing shortly after the Big Bang forces scientists to reconsider not only the timing of cosmic events but also the physical processes driving them. Moreover, the telescope's ability to peer into the atmospheres of exoplanets and detect the building blocks of life, such as water vapor, methane, and carbon dioxide, has expanded the search for habitable worlds. These discoveries could potentially reshape our understanding of life beyond Earth, adding a profound layer to humanity's quest to understand its place in the universe. Despite the excitement surrounding these breakthroughs, they also introduce a new level of complexity. For instance, the JWST has identified gravitational lensing phenomena, where light from distant objects is bent by massive intervening structures, such as galaxies or clusters. While these observations help astronomers map dark matter distribution, they also underscore the limitations of our current tools in distinguishing between intrinsic and lensing-induced features. The mounting evidence suggests that some cosmological principles may need revision. The S8 tension, Hubble tension, and the findings of JWST converge on a central issue. Our theoretical frameworks, while powerful, may be incomplete. This realization is not a failure but a hallmark of scientific progress. Each anomaly, each inconsistency, and each new observation is a step closer to a deeper understanding of the cosmos. Scientists are now calling for a multi-pronged approach to address these challenges. This includes revisiting the foundational assumptions of the lambda CDM model, refining observational techniques, and integrating data from various cutting-edge instruments, such as gravitational wave observatories and neutrino detectors. Collaboration across disciplines, from particle physics to astrophysics, is essential for piecing together the puzzle of the universe's origins and fate. As humanity stands on the cusp of a new era in space exploration, the James Webb Space Telescope serves as a beacon of hope and discovery. It reminds us that the universe is far more intricate and mysterious than we could have ever imagined. While the answers it provides may be unsettling or incomplete, they are also a testament to the boundless potential of human curiosity and ingenuity. New clarifications are demonstrating troublesome. The most recent disclosures are shaking the underpinnings of physical science, causing worry among numerous specialists. Physical science rules today are still heavily influenced by Isaac Newton's 17th-century work. For a prolonged period, his laws of motion and gravity have provided the foundation for understanding the physical world and the universe. Newton's laws worked splendidly under common conditions on Earth. However, in space, his ideas required expansion to an extraordinary degree, achieved by Albert Einstein during the 20th century. Einstein's theory of relativity, published in 1905, transformed our understanding of reality, showing that the laws of physical science are relative to the observer's motion. His general theory of relativity, published in 1915, expanded these ideas with mathematical evaluations of gravitational anomalies, considering the curvature of spacetime caused by masses like stars or galaxies. While Einstein's theories were groundbreaking in various areas, he recognized their limitations and sought a unifying framework, albeit without success. No scientist has yet prevailed in this endeavor. It is fascinating to consider where the errors could lie. Michio Kaku, a renowned American astrophysicist, suggested that solving this issue could lead to a Nobel Prize. "We genuinely need to examine what reality could have been misunderstood," he stated. Whether there have been misinterpretations of anomalies or whether telescopes themselves might be to blame, Dark matter and dark energy are top suspects in the cosmological crisis. Current models propose that dark matter and dark energy together account for nearly 95% of the universe. However, neither has been directly observed or proven to exist. They may not exist at all, or they may have properties we do not yet understand. One possibility being examined is that dark matter's properties could have evolved over time, perhaps showing some form of intelligence. Gravity, which should cause attraction through mass or spacetime, has not been directly shown to act exactly as expected. Despite the fact that spacetime curvature considerations from Einstein have been confirmed many times, we cannot fully rule out the possibility that gravity has extraordinary properties or that some other effect is causing gravitational attraction. Over time, specific properties in cosmology and space science have been established as key constants recognized for their consistency. Estimates suggest that small variations in these constants might offer new insights into the universe, potentially explaining phenomena without dark energy. It is also possible that our interpretations of light shifts have been incorrect, leading to mistaken distance estimations and galaxy ages. Perhaps our assumptions about the universe's conditions were flawed, or we misread the cosmic microwave background radiation. It could even be that the universe does not originate from a single starting point, challenging the Big Bang theory itself. Small errors in the Webb telescope or other observational instruments cannot be ruled out. Scientists and experts acknowledge that mistakes in instrumentation, data handling, or interpretation are always possible. The persistent reassessment of cosmological theories highlights the central nature of scientific progress, the ability to adapt and advance our understanding based on new evidence. The James Webb Space Telescope's findings represent much more than a technological leap. They mark a significant moment in our journey to unravel the universe's deepest realities. As we grapple with these discoveries, it is essential to consider the broader context and implications of such ongoing shifts in cosmology. The approach often involves refining theories according to new discoveries. The detection of unconventional phenomena or anomalies in established theories can be unsettling, but it also presents a tremendous opportunity for scientific advancement. Theoretical models in cosmology are created to provide a coherent framework for understanding the universe's origins, motion, and evolution. However, as new data emerges, these models must be tested and, if necessary, revised to accommodate new insights. One critical area of focus is the nature of dark matter and dark energy, which are crucial to contemporary cosmological models. Dark matter, a mysterious form of matter that does not emit or absorb light, was proposed to explain discrepancies between galaxy rotation curves and the mass predicted by observable matter alone. Similarly, dark energy was introduced to account for the observed accelerated expansion of the universe. However, despite their fundamental roles, both dark matter and dark energy remain elusive, with Earth-based experiments yet to definitively identify them. This has led experts to explore alternative theories and possible explanations. The challenge of understanding dark matter and dark energy is intensified by the immense scale of cosmological investigations, particularly when observing distant galaxies, the cosmic microwave background radiation, and other cosmic anomalies. While these provide indirect evidence of these components, their exact nature remains hidden. This uncertainty has prompted scientists to consider a range of theories, from modifications to existing models to entirely new paradigms. Some hypotheses suggest that dark matter could be composed of unusually exotic particles, or that dark energy could represent a new fundamental force. Another intriguing area of cosmological research is the study of cosmic inflation. This theory suggests that the universe underwent rapid expansion in its earliest moments, leading to the large-scale structure we observe today. While the inflationary theory has successfully explained many aspects of the universe, such as its homogeneity and flatness, it also raises questions about the nature of the inflationary period itself. Insights that challenge established models of inflation could lead to revisions in how we understand the universe's early history. Finally, the search for extraterrestrial life remains a primary driver of space exploration. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new avenues for studying the conditions necessary for life. Advances in
allow us to
telescope
understand
technology,
not only
such
the
as the
Big
James
Bang,
Webb
the Big
Space
Bang.
Telescope,
There may be
allow us
vast
to examine
regions
these
of the universe
exoplanets
that
for
we will
potential
never be able to
biomarkers.
observe.
The possibility
While
of
scientists
discovering
believe
life
that the
beyond Earth
universe
carries
stretches
profound
far beyond the
implications for how
observable
we
universe.
perceive the universe
In
and our
fact,
place within
it's
it.
possible
In
that the
conclusion,
entire light
the
years away,
reassessment of
meaning the
cosmological
observable
theories
universe
is a
is about
testament to the
94
strength
billion
of the
light years
scientific
across.
method.
This
The
might seem
James Webb
strange
Space
given
Telescope
scientists
and
need
other
to develop
advanced
a theory that
observational
merges these
instruments
two
have provided
frameworks. This
unprecedented
would allow us
insights
to
into the
understand
universe,
not only the Big
prompting
Bang,
scientists
but
to
also
revisit and
conditions that
refine
led to it.
long-held theories.
One of the most
This process
astounding
of continuous
aspects of the
inquiry
universe
and
is its
correction
size.
is essential
The
for
most
advancing
distant
our
objects we
understanding
can
of the
observe
universe
are the
and
early
addressing the
universe,
fundamental
and these
questions at the heart of
variations match
cosmology and
predictions
space
made by
science.
inflationary
As we
theory.
continue to
This
explore the
experimental
cosmos,
evidence
we
strengthens
are
the idea
engaged in
that
a quest
inflation
for
is not
knowledge
just a
that not only
theoretical
seeks
model,
to answer profound
but a crucial
questions,
part
but
of
also
how we
inspires
understand
future
the universe's
generations to
origins.
push the boundaries of human
Understanding the Big
understanding.
Bang in